So in a last video we have discussed about superconductor, and we have defined the superconductor as the material whose resistivity becomes zero is called as superconductor, which shows indefinite current flow without any attenuation, that is a superconductor. But this is a correct definition or not, that we will be cleared in some minutes. Okay, so before going into that aspect, we will study the Meissner effect. So what is the Meissner effect? The Meissner effect is simply stated as the explanation of the magnetic field by the superconductor. Okay, so this effect is simply differentiate between the perfect conductor and superconductor. So you can see in this figure, so at a room temperature, when you pass the magnetic field through a perfect conductor as well as superconductor, the magnetic field line will pass through the conductor as well as superconductor. But if you cool down the perfect conductor and if you pass the magnetic field line will still pass through the perfect conductor. But that doesn't happen in a superconductor. What happens if you cool down the superconductor below its critical temperature? The magnetic field line will not pass through the superconductor. The superconductor will explain the magnetic field, and the magnetic field will go around the superconductor. So this is nothing but a Meissner effect. The Meissner effect is nothing but the explanation of magnetic field lines by a superconductor. Alright. So this is a diagram which you have been seeing on a YouTube video or some social media content, that the magnet will leviate on a magnetic bar or magnetic disk. So why this happens? This is due to the Meissner effect. Okay, so we will go into some theoretical aspects now. So we know that this equation B is equal to mu 0 in bracket H plus M, where B is the magnetic induction, mu 0 is permeability, H is the magnetic field intensity, and M is the magnetization. So when your B is equal to 0, that will give us M by H, that is a magnetic susceptibility Xi is equal to -1, and negative susceptibility shows that the material is a diamagnetic. So we can conclude here that if B is equal to 0, then the superconductor will behave as a diamagnetic material. But B is equal to 0 does not follow from the resistivity 0. So how? That we will see now. So we know that Ohm's law is equal to J is equal to rho into E, or E is equal to rho into J. That is, E is the electric field, rho is a resistivity, J is a current density. So if rho is equal to 0 and J is equal to 0, then J will be finite, and that implies that E is equal to 0. Now we have the one more Maxwell equation, that is third Maxwell equation. The curl of E is equal to negative of gradient, the time derivative of magnetic field, that is curl of E is equal to minus dabba B by dabba T. And if your E is equal to 0, then dabba B by dabba T will be 0, and that implies that B is equal to constant. So there is a difference. So here B is a constant, B is not equal to 0. Okay, so the zero resistivity of the material magnetic induction is not necessarily 0. The B is equal to 0 is a special property of superconductor only. This is a strong repulsion of external magnetic field called as leviation effect, that whose image we have saw in a previous slide. Okay, so this simply what it means, that is concluded here. So not only the rho is equal to 0, that is a perfect conductivity, is a definition of superconductor, but if B is equal to also 0, that is the material is also showing the perfect diamagnetism, that will define the superconductivity. So in conclusion, what is a superconductor? The superconductor is a material who shows rho is equal to 0, that is perfect conductivity, that is no power loss, as well as B is equal to 0, that is perfect diamagnetism, that is strong repulsion of magnetic field. The only rho is equal to 0 does not make any material superconductor, it should obey both the property, that is rho is equal to 0, and b is equal to 0. That is, the superconductor is perfect conductor with a perfect diamagnetism. So that is a proper and correct definition of superconductor. Thank you.